Now we shall move on to session 2 titled Metamaterial Inspired Antennas for Compact and a Performance System. It is indeed a great honor to introduce our resource person, Dr. K. Krishnamurthy, Associate Professor in Department of Electronics and Communication Engineering at NIT Karnataka, Suratkal. Dr. Krishnamurthy is an accomplished academician and researcher specializing in antenna design, reconfigurable and multiband antenna, RF and microwave engineering, and metamaterial and meta surfaces. He obtained his PhD in electrical engineering from IIT Bombay since joining NIT Suratkal in 2009. Dr. Krishnamurthy have been actively involved in teaching, research, and mentoring students in advanced areas of antenna and wireless communication. He has successfully executed several funded projects, includes compact multiband antenna with independently controlled resonant frequency and polarization for mobile wireless application funded by SERB DSD Government of India with the project cost of rupees 44 lakhs and design and development of wideband circular polarized antenna using 2D metamaterial structures sponsored by ISRO, a response scheme with the cost of rupees 25 lakhs and currently a multifunctional meta surface design for amplitude polarization and a wavefront control for 6G communication system funded by SERB under DST with a project cost of rupees 30 lakhs. His notable projects include pioneering work on compact reconfigurable antenna, circularly polarized metamaterial based antennas, and intelligent reflective surface for next generation 6G systems. Dr. Krishnamurthy has published over 60 plus research papers in reputed international journals and IEEE conferences. His research have earned wide recognition, and his research group at NITK has produced award-winning PhD thesis, including recipients of BIT's Best PhD Thesis Award and a Special Jury Mention Award. In addition to his research achievements, Dr. Krishnamurthy is deeply committed to mentoring young researchers and fostering innovation in antenna designs and communication system. We are truly privileged to have Dr. K. Krishnamurthy with us today. Over to you, sir, for this technical session.
So thank you for your nice introduction. Thank you for the opportunity to present the topic of metamaterial antennas for high performance systems. Good evening to all. Myself, Krishnamurthy K, working as Associate Professor at NITK Suratkal in the Department of Electronics and Communication Engineering. So today, my presentation topic is metamaterial inspired antennas for compact and high performance systems. Under this topic, today we are going to cover the introduction to metamaterial, concept to reality, how to realize the metamaterial structures, okay, and what are all the commonly used structures for metamaterial, and the metamaterial applications in the area of antenna design, particularly for UWB antenna, the beam tilting applications, polarization conversion application, then multi-band circularly polarized antenna design, and also finally we are going to discuss about the MIMO antenna, multi-input, multi-output antenna. This is one of the technique. It is the most fundamental technique for the 5G communication systems. So first of all, we will see the metamaterial introduction. So what is metamaterial? So metamaterial is nothing but is a periodic arrangement of metal or some dielectric structures, okay, and also it is related with the wavelength of operation. So it is a sub-wavelength structure. Okay, the wavelength is much smaller to the operating frequency. The structure length is Okay, the dimension of the structure is much smaller than the wavelength, sub-wavelength structure. Okay, if you are arranging in the periodic manner, so what it is going to happen that whenever the electromagnetic wave is incident on this structure, so it is going to behave as a meta atom. So we know that the conventional material, naturally available material, it is made up of atoms. Okay, so whenever electromagnetic wave is incident on the any material, so what it is going to happen in case of dielectric, so we have the displacement of the atom gets enlarged actually. Okay, so because of that, so we have that some dipole moment it is going to form. So what is the ability of the dipole moment formation inside the material? It is going to define the dielectric constant. Okay, the dielectric constant we can able to define that uh, the amount of dipole moment formation inside the atom when the electromagnetic wave is formed. So similar to that, so in the in our meta atoms also, whenever electromagnetic wave is incident, so it is going to interact with the electric field and magnetic field, and the material it is going to give some kind of response to the incoming electromagnetic wave, and it is going to exhibit some unusual properties compared to the naturally available atoms. So we can able to get the simultaneous negative permeability and permittivity characteristics. Okay, so that kind of behavior we call it as the metamaterial here. So we know that the material characteristics we are going to classify based on the epsilon and mu characteristics. So we are going to divide that all the material into four categories. Okay, when epsilon is greater than zero and mu is greater than zero, that we called as a double positive material. This we called as a conventional material. So all the dielectric materials conventionally available is going to exhibit this kind of behavior. Okay, the permittivity and permeability is always positive and greater than zero here. So in this case, we have that the propagation constant or wave number k is real, and the refractive index n also it is going to be real for this kind of material. Okay, the next category of material, so here we are having that epsilon value, the permittivity is negative and permeability is positive here. So this we call as a single negative medium. Okay, so example for this kind of medium, this also naturally available at high frequencies like plasmas and metallic rod. Okay, the metallic array of metallic rods at particular frequency, it is going to exhibit this kind of characteristics. So here if you see that the wave characteristics, suppose that the propagation constant or wave number and the refractive index. So this wave number and refractive index is going to tell that the characteristics of the wave. Okay, so how much wave it is going to propagate and what direction it is going to propagate. So all those things, the velocity of the wave. So all those things it is going to characterized by this k and n. So by why we are interested in this k and n propagation constant or wave vector and this refractive index, so we can able to manipulate the electromagnetic wave, whatever that characteristics we want, we can able to manipulate by like the polarization conversion, then the beam focusing, then beam tilting. So all those this kind of characteristics we can able to easily we can able to manipulate the electromagnetic wave to achieve the desired characteristics. So by controlling this k and n in terms of by controlling this epsilon and mu. Okay. So another category of the material we call it as epsilon negative and mu negative. Both simultaneously it is going to be negative values that we call it as the double negative medium. So the example for the double negative medium is the combination of the split ring and the metallic rods. If you are arranging periodically these two combinations, so we can able to achieve this kind of characteristics. So here also you can able to see here the wave number k is real as well as the refractive index n also it is going to be real. So it is going to behave the similar to the double negative medium. So whenever this real k and real n we are going to have, there we have the wave propagation. Okay. So in the double positive as well as double negative medium, the wave is going to propagate, but we are going to have the some unusual characteristics compared to the positive double positive medium. Okay. The double negative medium, it is going to offer that unusual characteristics compared to the double positive medium, but the wave is going to propagate in both kind of medium. But in the single negative medium, either the mu negative or epsilon negative medium, the wave cannot propagate inside that particular medium here. Okay, the fourth category of the medium, here it is epsilon is positive, but mu is going to be negative. So here also we have the complex k and the complex n here. Here also wave cannot able to propagate. The next slide here, this shows. So what is the wave characteristics? The wave is entering, electromagnetic wave is entering from air to this particular medium. In case of double negative and double positive medium, so we can have that the wave is going to propagate here. But in case of single negative medium, either epsilon going to be negative or mu going to be negative. In this case, the wave cannot propagate inside the single negative medium. It's going to be exponentially decaying case. Okay. So this is the characteristics of the material properties for the electromagnetic wave for the double negative and double positive and single negative medium. So you can able to see here in this slide that so what kind of behavior it is going to give for the double positive medium and the double negative medium. Okay, in the double positive medium, so whenever the wave is entering from the air to that particular medium, okay, it is going to obey that Snell's law. Okay, so we have the refraction and reflection of the electromagnetic energy. It is going to happen at the junction between the air and medium interface. Double positive medium, it is going to offer the it is going to obey the Snell's law. But the double negative medium, so here it is going to have that opposite effect here compared to the conventional material. Okay, here also wave it is going to propagate, but you can see the direction of the wave propagation. Okay, so at the interface, so we are going to have the negative refraction. So conventional material, it is going to offer the positive refraction. The double negative medium, it is going to offer that negative refraction. So here you can see that the wave it is going to propagate in the conventional material. So in the particular direction according to the Snell's law. But here that opposite to the direction that wave shifted the direction, the wave number, wave vector direction, it is going to be have in the opposite direction here. This we called as a negative refraction here. So in the single negative medium, the wave cannot able to propagate. It is we have the complete reflection at this mediums here. Okay. So the conventional medium, it is going to obey uh, that right hand rule. Okay. That double negative medium, it is going to obey that left hand rule. So this medium material, sometimes we used to call as left hand material. This conventional medium is sometimes used to call as right hand material. Okay, so if you take that right hand, the thumb and the index finger and the pointing finger and all those things, so as the electric field, magnetic field, and this direction of k vector, so it is going to obey that right hand rule, and this method we called as the forward wave propagation. Okay, so in case of double negative medium, it is going to obey that the left hand rule. So kind of wave propagation we called as the backward wave propagation. Okay, the compared to this positive medium, the wave propagation direction is changed. So that's what we called as the backward wave propagation here. So this figure, particular figure, it shows that clearly that the direction of wave propagation and energy propagation. Okay, so in the double positive medium, the k vector and the pointing vector s in the same direction. Yeah, that means that phase velocity and group velocity are in the same direction. Okay? So that we call as the forward wave propagation. But in case of the double negative medium, okay, So in case of the double negative medium, so we have that the K is propagating in one particular direction, opposite direction to the pointing vector S here. The energy actually it is flowing opposite to the phase propagation here. Okay, so that's what we call it as this one as the backward wave propagation. Okay, so if you see that compared to the forward wave and the conventional and the left hand medium and right hand medium, that the refraction it is going to be look like this. This entirely that opposite direction here. This is the conventional medium. So this one is the uh, the double negative medium. Okay. So these are all the properties of the double negative medium. So using this unconventional wave behavior inside the double negative medium, so we can able to utilize this kind of behavior to achieve some unusual behavior of the electromagnetic wave, so that we can able to control and manipulate the electromagnetic wave. So as per our requirement. So using this behavior, so we can able to design some antenna applications for polarization control and the wave beam focusing control. So like that, so many applications we can able to design. So we are going to see the some of the applications, particularly for the antenna design applications. So how we can able to get that double negative medium? Okay, so we know that the single negative medium it is naturally it is available at particular frequency of operation. So we can naturally epsilon negative is available and mu negative also it is available. If you want to get mu negative value, okay, so we can get by using this kind of arrangement. So if whenever if you are going to arrange the metallic rod in the periodic arrangement, okay, so we can able to get at particular frequency, the frequency also we can able to determine using that the periodicity and the radius of the rod. Using that we can able to change the uh, frequency of the negative refractive index, the negative permittivity here. Okay, so whenever if you require that negative epsilon value, so we can use this kind of arrangement. So this arrangement is going to give that uh, permittivity negative value here. So we can able to calculate at what frequency we can able to get that the negative the plasma frequency we can able to calculate the plasma frequency. It is going to determine at what frequency, so we can get this value epsilon going to be the negative here. So similarly, whenever if you want the mu negative value, that kind of characteristics we can able to realize using the split rings. Okay, whenever if you are going to use this periodic arrangement of the split ring, then if the incident electromagnetic wave has the orientation of the magnetic field, okay, in the axial direction of the ring as given in this figure, so we can able to get the mu. Also it is going to be the negative at particular value of frequencies. At what value of frequency we can get the mu value negative, that we can able to control by adjusting that radius and split gap with all those things using this material that unit cell parameters. So we can able to control the resonance frequency where we can able to get the mu negative. So these two characteristics are independently it is available, naturally it is available. But uh, if you want to design that left hand material or double negative medium, that is not available naturally. Okay. So whenever if you want to get the double negative, so we have to implement using that rod, metallic rod and ring, these combinations we have to design. Okay. So this we call it as artificial material. So we can get that artificially the mu negative and epsilon negative value, okay, at particular frequency simultaneously both the values are negative. It is not available naturally, okay, in any material. So this kind of characteristics we can able to get artificially or man-made structures, okay, this kind of structures, so we can able to get. Okay, so the epsilon negative value, so we already know we can able to get using the periodic arrangement of rods, and we can able to get mu negative value using the split rings. Okay, so it is proposed by Pentre in 1999. Similarly, the 1996 this epsilon negative was demonstrated. Okay. So until 2001, okay, so this double negative medium was not realized. Okay, so the Smith et al., the Duke University, they realized using this combination of these two structures, rod and split ring, they could able to achieve that the double negative medium simultaneously at particular frequency. They can able to achieve that epsilon zero as well as mu zero. Okay, so this kind of mu zero epsilon zero, it is going to give that some unusual characteristics like the left hand wave propagation, negative refraction, so all these characteristics. So this kind of material, this kind of medium, we call it as the metamaterial. Okay, the meta means beyond the unusual characteristics. Okay, so we can able to control that unusually the electromagnetic waves, and also we can able to manipulate the electromagnetic wave propagation and polarization by using this kind of materials. So we can able to get these metamaterial characteristics using this kind of four categories of structures. Okay, so we can have that negative mu we can able to get using this split ring and the periodic arrangement of slots here. Okay, these two structure, it is going to give that mu negative value, and the periodic arrangement of metallic rods and the complementary split ring. These two structure, it's going to give that epsilon negative value. The combination of these structures, we can able to get that simultaneous mu zero and mu epsilon zero values that we called as the metamaterials here. Okay. So these are all the engineering applications of the metamaterials. We are we can use along with the antennas to enhance the gain of the antenna and to reduce the size of the antenna. So all those things. So so here you can see that this is the combination of the slot and metallic rod. So this structure we call it as the electromagnetic band gap structure. That this structure, it is going to give some certain properties, okay, at particular value of frequency. So it is going to offer that the band gap to the electromagnetic wave. Okay. So whenever the electromagnetic wave is incident upon this kind of frequency region where the band gap is going to produced, so the electromagnetic wave cannot propagate inside the material. Okay. So similarly, this kind of structure, this mushroom structure, this structure we call it as band gap structure or electromagnetic band gap structure or mushroom structure because this look like the mushroom shape. So this we call as the mushroom structure or electromagnetic band gap structure. This is going to give the electromagnetic band gap property as well as artificial magnetic conductor property. Okay, so we have naturally the electric conductor. So we don't have naturally the artificially magnetic conductor. We don't have the naturally magnetic conductor. Okay, so this medium, it is going to give the property of artificial magnetic conductor. Okay, so it is going to behave as the magnetic conductor. What is the property of the electric conductor? Whenever the electromagnetic wave is incidenting, so inside any metal, okay, what it is going to happen? The electromagnetic wave, it is going to completely reflected back with 180-degree phase shift. So that we call as the electric conductor. So in case of magnetic conductor, if it is available naturally, it is going to give the complete reflection, but with the 0-degree phase shift, the reflection phase, the incident phase and the reflection phase of the electromagnetic wave is going to be same, electric field. But that kind of conductor, it is not available naturally. Okay, so this mushroom structure is going to give that the zero reflection phase at particular value of frequencies, so that we call as the artificially magnetic conductor. So using the artificial magnetic conductor, so we can able to get uh, we can able to use along with the antenna, the dipole antenna here. So it is shown here this we can able to reduce the antenna profile height actually here. Okay. So whenever if we want to avoid the back radiation for any from the dipole antenna, we are using the metallic conductor. So if we want to use the metallic conductor, we have to use the gap between the antenna and the conductor of the lambda by 4 to get the maximum radiation in the broadside direction. Okay. So the same kind of performance we can able to get using this kind of artificially magnetic conductor without any gap here because of the zero reflection phase here. Okay. So the antenna height we can able to reduce here. This lambda by 4 height requirement for the metallic conductor we can able to avoid by using the uh, artificial magnetic conductor here. Similarly, the electromagnetic band gap property of the mushroom structure is used to control the surface wave of the microstrip patch antenna so that we can able to improve the radiation characteristics of the microstrip patch antenna. Here, the side loops we can able to reduce here. So you see the conventional microstrip patch antenna here. So we have the finite ground plane. So whenever we have the finite ground plane, we have the surface waves. The surface waves are going to propagate and it's going to radiate in the unwanted direction. So we have the some side loops other effect. The side loops, if we want to minimize, then we can use that the electromagnetic band gap structure here, okay, around the microstrip patch antenna in the substrate. Then what it is going to happen that the electromagnetic band gap structure it is going to give the band gap effect in the resonance frequency of the microstrip patch antenna. It is going to control the surface wave propagation inside the substrate. Okay. So then we can have that the only the main loop it is going to main loop, my only main loop it is going to radiate in the broadside direction. So we can able to eliminate the side loops here. Okay, these are all the some of the applications of the this kind of double negative medium that we call as the metamaterials here. So using the two-dimensional equivalent of the metamaterial, we call it as the meta surface. So using the meta surface, we can able to get so many applications like the polarization conversion, then the beam steering effect, the beam control effect, and all those things. So whenever the linearly polarized wave is incidenting, okay, either the reflected wave or transmitted wave, we can able to convert to circularly polarized wave. Okay. So if one type of polarization is incidenting, either the reflected or transmitted wave, we can able to convert into other type of polarization. So this kind of application, we can easily use the conventional simple antenna to produce the circularly polarized radiation, the antenna applications. Okay. So the fundamentals of antenna is nothing but, so whenever if we have the static charge, it cannot able to radiate. Okay. So it can produce the static electric field. So we know from the static electrostatic effect. So we already studied it's going to obey the Coulomb's law. Okay. According to that, it's going to emit the electric field. So the electric field is a static field. So it cannot produce the time varying electromagnetic wave. And similarly, whenever the electric charge is moving with uniform velocity, so this kind of movement also cannot able to produce the electromagnetic wave. Okay, whenever the electric charge is moving with constant uniform velocity, so it can able to produce the according to the Ampere's law. So we can able to get that steady static magnetic field. Okay, so whenever the charge is getting accelerated inside the medium, so we can able to get that it's going to produce that the time varying electric field, and the time varying electric field it is going to produce the time varying magnetic field. Then we are going to have the electromagnetic wave. Okay, so like this in case of the dipole antenna, so whenever the oscillating electric current is flowing to the dipole, so we can have this kind of the electric field and the electric charges, positive and negative charges are separated like this way, and it is going to oscillate. Okay, this oscillation, it is going to create that the time varying electric field. The time varying electric field again, it's going to create the time varying magnetic field. So we can have the electromagnetic radiation. So whenever if you want to create the electromagnetic radiation, so we should accelerate the charge. Okay, so the electromagnetic wave, it is going to maximum radiation, it is going to occur that the perpendicular to the direction of the acceleration. Okay, in the dipole antenna, it is going to accelerate in this direction, but the maximum radiation, it is going to happen the perpendicular to the direction of the acceleration of the charge. Okay. So whenever if you want to produce the electromagnetic wave in the particular direction, so accordingly we have to accelerate the charge in particular direction so that we can able to produce the electromagnetic wave so in particular direction. So what is the purpose of the antenna? The antenna should radiate the energy, electromagnetic energy, to the particular direction in the space. Okay, it should not radiate all over the directions. So it has to produce the electromagnetic wave only in the intended direction. So to send the electromagnetic wave in a particular direction, so we have to accelerate the charge in particular the direction so that we can able to produce the electromagnetic wave in the particular direction. So based on this, so we can have the we can able to design the antenna for the particular applications. Okay. So the antenna is nothing but is the device, it is used to transmit and receive an electromagnetic wave. The antenna is a passive device. The same antenna we can able to use for the transmission as well as the reception purpose. Okay. So if you take any wireless applications, the antenna is the device. Okay. So it is there in the both the transmitter as well as in the receiver. So we know that whenever we are using the antenna in the free space communication from the transmitter to the receiver, if the distance is r, so we have that if we are using the antenna, the power is reducing with the ratio of 1 by r square. Okay, if the transmitter power is something with p, the received power, it is reduced by r square with the distance r. The similar way, if we are using any the wave guiding system instead of antenna, if we are using any wired medium, okay, the power is exponentially, it is getting decayed. The decay rate of alpha, okay, the alpha is the decay rate. It is going to determine by the characteristics of the material. Suppose if we take the coaxial cable or fiber optic cable, so we have the attenuation constant. So this attenuation constant, it is going to determine that exponential decay factor here. But in case of antenna, the power is reduced by that 1 by r square ratio. So in case of for the long distances, instead of using the cables, we can use the antenna for that less loss actually. Okay. So if you are using the short range communication, so we can go for the guided medium. For the long distance communication, so instead of using that exponential decay, is 1 by r square, it is going to give that less loss compared to the guided medium here. So the antennas, if you want to design, we are having that some main properties of the antennas. Based on these properties, so these are all the some specification, design specifications of the antenna. That is the radiation pattern, the directivity, okay, the efficiency, the polarization, the bandwidth, the input impedances. So these are all the specifications or properties of the antenna. So if these values are known, then we can able to design the particular the antenna here. The mainly the directivity gain, then the bandwidth, all those things are the input for the antenna designers. So using this specification values, so we can able to design the antenna for particular applications. So by using the metamaterial concept, so we can able to design some of the antennas. Okay, we can able to improve the antenna characteristics. So the first example is the metamaterial based antenna for UWB applications. So here this is the conventional UWB antenna. It is loaded with the metamaterial inspired structure. So to produce some band notches in the UWB antenna and the reconfigurable band notches in the UWB antennas. Okay. So we know that UWB antenna, it is going to radiate from 3 gigahertz to 10 gigahertz, the ultra wide bandwidth. Okay. So within this UWB band, so we have that our Wi-Fi also it is there, and some other standards, wireless standard also it is there. Okay. So these bands we have to be notched out. So we have to remove this band from the ultra wide band. So for that, we are using this kind of metamaterial inspired structures like the split ring and the mushroom structures. Okay. So to create the band notches in the UWB antennas here. Okay. So this split ring, it is going to give that uh, fixed band notches. And here we are using the UWB, that we are using the mushroom structure, two mushroom structure, okay, the side by side along the feed line. And this mushroom structure, it is reconfigurable. So you see the front view and back view. The back view, we are using some switches, S1, S2, and S3 pin diode switches we are using here, so that we can able to change the via position of the mushroom structure. Okay, this is the via position of the mushroom structure here. So we can able to on and off the vias here. So whenever we are going to on and off the vias, so we can able to reconfigure the position of the band notch in the UWB antenna. This is the equivalent circuit of the mushroom structure loaded with the microstrip antenna, microstrip line here. Okay, this is going to be act as the parallel LC circuit here. So whenever that at the resonance frequency of the mushroom structure, we have the band gap. So that band gap is going to stop the electromagnetic wave propagation in the in the microstrip line. So because of that, we can stop the electromagnetic wave radiation at particular frequency of operation, so that we can able to create the band notch. So here the two vias are there in particular mushroom structure, the edge via and the center via. Whenever the edge via is there, this electromagnetic band gap structure is going to produce band gap at particular frequency. Whenever that center via is there, we are going to shift the band gap frequencies. So using these characteristics, so we can able to get the band notch characteristics in the UWB antenna. So this is the simulation and measurement results when the different switching configurations. Okay, this is the VSWR plot of the UWB antenna. Okay, this is the UWB antenna. It is going to give the three band notches. Okay, at any switching position, it is going to give the three band notches. One band notch it is going to come from the split ring. Another two band notches it is going to come from the mushroom structures loaded with the UWB antenna. So by changing the switching positions on and off, so we can able to change the band notch positions. So another one is the design of UWB antenna using the slot antenna. So we have seen the many UWB antennas in the literature using the monopole configuration, but we try to design the UWB antenna using the slot antenna. Okay? By loading the artificial transmission lines onto the slot antenna. This is the slot antenna, conventional slot antenna. This slot antenna is loaded with this kind of artificial transmission line. Okay, this is the transmission line. This transmission line is loaded with the slots. Here, periodic slots are loaded on the transmission line. This structure, it is going to give the some band gap nature. Okay, so that resonance frequency we can able to control by changing the this gap width actually. Okay, but what we are going to do in this slot antenna, we are going to loaded with this slot antenna is loaded with the this kind of artificial transmission line with different width. This is one transmission line, this is another transmission line, this one is another transmission line, this one is another transmission line. The gap in the transmission line, it is going to gradually it is going to vary. Okay, so that so this gap variation it is going to give that different resonance frequencies. Okay, So this different resonance frequency is going to give the wide bandwidth in the slot resonance. The loading of the artificial transmission line on the slot antenna is going to give the some resonance characteristics in the slot. Okay, so the each transmission line it's going to give the different resonances as shown in this uh, return loss characteristics of the antenna. So we are having the multiple resonances. The resonances are close to each other so that we can able to get that wide uh, band of wide band characteristics so that we can able to get the ultra wide band characteristics of the slot antenna here. Okay. So these two applications we have realized using the metamaterial inspired structures to design the UWB antenna for the band notch characteristics and UWB characteristics with the slot antenna. Okay. So the next application is the beam tilting applications. This is a simple dipole antenna here. Okay. So the dipole arms are printed back to back. So this is the one arm of the dipole, that the other arm of the dipole is printed on the back side of the substrate. Okay. This is the ground plane for the dipole antenna here. Okay. This is the conventional dipole antenna. This conventional dipole antenna is loaded with this kind of the electromagnetic band cap structure. Okay, here you can see that electromagnetic band cap structures. So some of the electromagnetic band gap structures are the center loaded vias are there here. Okay, so only these two columns, okay, the vias are loaded with the edges here. Okay. So this edge loaded vias it is going to produce some kind of reflection characteristics compared to the center loaded via characteristics, so that we can able to tilt the electromagnetic wave the desired direction. So this radiation pattern, the 3D simulated radiation pattern is for the uniform via. So all the vias are center loaded. Then we can able to get the electromagnetic wave radiation in the broadside direction. Okay. So whenever the vias are uh, these two columns of the electromagnetic band cap structures, the vias are loaded at the edge, then we can able to tilt the beam towards the x direction here. Okay, similarly, whenever if you want to tilt the beam in the other direction, so on the particular direction, so we can able to shift the vias to the edge, then we can able to tilt the beam to the desired direction. Okay, so here this the gain plot it's going to give the different position from the center, the via position. We can able to tilt the beam to the different directions here. Okay, the different angle from the broadside direction. So advantage of this antenna is, so we can able to get the unidirectional radiation pattern, that is the broadside direction. The back radiation we are minimizing, and that height of the ground plane also we are reducing. If we are using the conventional uh, conductor as the ground plane, so we have to use the lambda by 4 distance between the dipole antenna and the ground plane. Okay, to get that constructive interference in the broadside direction. So this mushroom structure or electromagnetic band cap structure, so it is going to be acting as the artificial magnetic conductor. Okay, so that we can able to give the very close to the antenna without any lambda by 4 distance. So we can keep the ground plane very close to the antenna so that we can able to minimize the antenna height, and by controlling the via positions, so we can able to tilt the beam to the desired direction also. Okay, so using this kind of antenna configuration, so we can able to achieve the multi-functions using the same structure, so we can able to get the multi-functions. So what improvement we can able to do this kind of antenna? Here also we can able to use the reconfiguration, the via position reconfiguration by connecting the switches in the vias, so we can able to dynamically we can able to reconfigure the radiation to the desired direction. So here we tried for the fixed direction. Okay, we want to direct the beam to the 45-degree or 30-degree from the broadside. So accordingly we can keep the via position then the antenna can radiate to the fixed direction. By connecting the pin diode switches, so we can able to radiate the beam dynamically to the different directions also. So here, this is the metamaterial loaded slot antenna for the polarization reconfiguration applications here. Okay, this antenna, this is the simple slot antenna here. Okay, this is the slot and this is the feed line. Okay, this slot antenna is loaded with this kind of metamaterial structure. Okay, by loading this metamaterial structure, so what we can able to do, we can able to convert the polarization from one linear polarization to circular polarization. The circular polarization also is the different polarization we can able to reconfigure. So by rotating this metamaterial structure with respect to the center of the slot, okay, so if the position of the metamaterial structure is like this way, it is going to give the left-hand circular polarization. Okay. So if you are going to rotate along this direction, okay, mechanically, if you are going to rotate, then if the rotation it is going to be reaching along this direction, so we can able to get the right-hand circular polarization using this antenna. So we can able to reconfigure the polarization simply by rotating the metamaterial structure with the slot antenna. So we can able to get the different polarization. So we can convert the simple linear polarization slot antenna to circular polarized antenna. And also we can able to control the polarization sense simply by rotating the metamaterial structures with respect to the slot. We can able to control the polarization sense, the left hand circular polarization as well as the right hand circular polarization. And this antenna is going to give the low radar cross section also. This also is a multifunctional antenna. Okay. It is going to give the polarization reconfiguration as well as the radar cross section reduction. Okay. So by loading the metamaterial structure onto the slot antenna, so we can able to reduce the radar cross section of the antenna. The radar cross section is very important in the stealth applications. So when the antenna we are going to use for the submarine ships or any other military communication equipment, okay, so that equipment should give that less scattering. Whenever the electromagnetic wave is incidenting, that reflection should be minimized. Okay. So the antenna also it is part of the equipment. The antenna also should give the very less reflection. So whenever the radar cross section is very low, then that reflection coming from the antenna also it is very low. Then the detectability of the structure also it is minimized. So we cannot able to detect the equipment or any other structure if the radar cross section is low. So this kind of applications, so we can use this kind of structure. So the compared to the conventional slot antenna, okay, the RCS performance is so much it is improved, more than 15 dB improvement it is we able to get by using this kind of the metamaterial structures here. So here we can able to get both RCS reduction as well as the polarization conversion using this kind of structures, and also we can able to reconfigure the polarization sense. So the next one is that the circular polarization antenna we can able to design with reduced radar cross section. So this is the metamaterial structures we are using here. This is the conventional array of the rectangular patch and patch structures here. So this structure, if you are going to load it with the conventional slot antenna, so this structure it's going to give that it's going to convert the circularly polarized, linearly polarized radiation of the slot antenna to the circularly polarized antenna, as well as it's going to give the reduced radar cross section. Okay, that's similar to the previous structure. So here we are using that the simple array of patches as the meta surface. That meta surface is loaded with the slot antenna. This combination of this structure with the slot antenna is going to give the circular polarized radiation with reduced radar cross section here. So we can show here that the XL ratio bandwidth and the impedance bandwidth, the return loss bandwidth, and the radiation characteristics here. So in the any wireless communication, that the gain, the improvement, it is going to be required for any antenna, because the gain improvement, it is going to give that more the signal to noise ratio, and it is going to give that better the bit error rate performance for the communication system. Okay. So the power is one of the resource of the wireless communication, similar to the bandwidth. Okay. So the antenna gain is more, so we can able to operate with the low power also to get the desired bit error rate performance. So the antennas always should give that high gain. Okay. So here we are going to improve the conventional antenna gain. So to improve the antenna gain, conventionally we are going to use the array of antennas. Okay, so we are going to use the rectangular array or linear array, that kind of arraying technique. So there we have to use the feed lines. Okay, we have to use the feed lines for the individual structures, and maintaining the feed line and everything, it is going to be difficult. And also we have to give the proper uh, phase for the each individual array element, the maintaining the phase, amplitude, and all those things, everything is going to be difficult for the large array. So here we are going to use for the simple single patch antenna. This patch antenna is going to be loaded with this kind of meta surface. Okay, so this meta surface is going to be acting as the lens kind of operation, so that it is going to give that improved gain for the single patch antenna. So here we are not going to use any feed structure or complex feed structure or multiple antenna element. The single antenna element, the simple feed structure we are using. This antenna, single antenna, is loaded with this kind of the meta structure here. This element, it is going to give that lens kind of operation, because this is going to give that that near zero refractive index. The refractive index of this kind of material we have calculated here, it's shown here. The refractive index, it's going to be near zero. Okay, so both epsilon and mu value, it is going to be near zero, less than 1. So this is going to give that near zero index refractive index. This kind of structure, it is going to give some kind of focusing effect for the electromagnetic wave. So the radiation coming from the patch antenna, it is going to be focused using this the meta surface structure. Then we can going to get the improved gain. Okay, so this is the return loss plot for the meta structure loaded the patch antenna, and this is the axial ratio gain. And other than giving the gain, this structure, it is going to give simultaneously, it is going to convert the linear polarization to the circular polarization. Okay, so both the gain enhancement as well as polarization conversion, it is going to happen in this structure. So we can have that circular polarization characteristics as well as the gain improvement here. Okay, so we are getting the gain of around the 15 dB here using the single patch antenna. The conventional microstrip patch antenna, it is going to give the 6 dB gain, 6 dBi gain. So here we can able to get that almost to the 10 dB improvement using this kind of structure, as well as we can able to convert the linear polarization of the patch antenna into the circular polarization. So using the metamaterial structures, we can able to get that the dual band, dual circular polarization. Okay, the dual band operation, multi-band operation, we can able to get. The both the bands, we can able to achieve the circular polarization. So here the simple microstrip slot antenna, it is loaded with this kind of connected SRRs. Okay, this kind of connected split ring resonators are loaded. The connection you can see here, this the view of the split ring resonators. Okay, the split ring resonators are characterized. Okay, for particular resonance frequency. So whatever the resonance frequency we need, the antenna should resonance. So we can able to characterize the split ring resonators. So we can able to adjust the ring radius and the gap width and all those things, so that we can able to get that particular resonance frequency. So we have designed for the 4.5 gigahertz. Okay, this is the characteristics of the split ring. This split ring is loaded with the simple microstrip slot antenna here. The slot antenna also, it is here that here what it is happened, that the corners are sorted here. Okay, these corners are sorted. So this arrangement it's going to give that dual uh, band resonance, as well as both the bands we can able to get the circular polarization. Okay. So this is the different configurations of the slot antenna. There is a simple conventional slot antenna is going to give us one resonance frequency. Okay, here at this resonance frequency. So if you are going to get this kind of corner started slot antenna, it is going to give that again the single resonance. If you are going to load it with the split ring, we can get the dual band. Okay, the dual band. That both the bands is going to give the linear polarization. So this is the axial ratio bandwidth for the different configuration is shown here. But the corner sorted, the loaded with the connected split ring, this configuration it is going to give the dual band with circular polarization. Okay, so this is the electric field distribution at the different time instant here. Okay. So using this electric field distribution, so we can able to confirm that this the electric field it is going to be rotated when the time progress. So we can able to get the circular polarized antennas here. Okay, so this is the uh, simulated and measured return loss characteristics of the final antenna. So here we can get the dual resonance frequency, and using this axial ratio plot, we can able to confirm that the both the bands we can able to get the circular polarization here. Okay. So the gain also we can get the reasonable gain around the 6 dB gain for this antenna. This is the radiation pattern. You see here the radiation pattern is going to give that because this is a conventional slot antenna, so it is going to give the radiation pattern of the bidirectional radiation pattern. The radiation it is going in the forward direction as well as in the backward direction. So if you want to avoid the backward wave propagation, the direction, the radiation, then we can able to put some cavity structure. Then we can able to reduce the backward radiation. So that also we have tried here. Okay. So this is the dual band circularly polarized antenna with metal cavity here. So we have connected the metal cavity, the one side of the antenna, to reduce the backward radiation. Okay. This is the side view of the cavity connected the antenna to the antenna. So you can see that the axial ratio and the impedance bandwidth is not affected because of the cavity loading, but we can able to improve the radiation characteristics for the circularly polarized antenna here. So for the both lower band and the upper band, the radiation is the unidirectional. So we can the only the broadside radiation it is there, and we can able to improve the gain also in the broadside direction because the back radiation we have minimized here. Okay, so the antenna it is going to radiate only in the broadside direction with improved gain compared to the simple antenna loaded with the SRR here. So using the metamaterial inspired structures, so we can able to design the multi-band antenna with the multiple functionalities. Okay, so this is the simple conventional monopole antenna. Okay, so this monopole antenna is loaded with the metamaterial inspired structures to create the multi-band operation as well as the compactness here. Okay, so this ground plane of the monopole also it is loaded with this kind of slots. and this antenna is loaded in the back side with the one split ring and in the front side with the meandering structure. Okay. So the loading of the meandering structure, this split ring, and this ground plane, the modified ground plane, this structure, it is going to give one resonance frequencies. This antenna is going to give the triple band resonance. Okay, so the meandering structure loading is going to give one band, and this SRR it is going to give the another band, and the modified ground plane is going to give the third resonance frequencies here. So another advantage of this antenna is, so we can able to independently tune one of the resonance frequencies without affecting the other resonance frequencies. Okay, suppose I want to tune the resonance frequency of the third band. So what I can able to do, I can able to adjust the depth of this ground plane modification or this width of the this gaps. I can able to adjust. So I can able to reconfigure only the third band. These two bands are we can able to keep fixed. So similarly, the center band I want to reconfigure. So what I can able to do, I can able to adjust the parameter of the split ring. Okay. So in that case, the other first and third band we can able to fix the same value. Similarly, the first band, if I want to change, means I can able to change the parameter of this meandering structure. So I can able to change only the first resonance frequencies. The other two resonance frequencies we can able to fix the same. Okay. So this kind of independently tuned triple band antenna also we can able to design, and this structure is going to be the very compact structure. Okay, according to the first resonance frequency, this structure is the compact structure, and we can able to get that tri-band operation using this uh, structure. Okay. So this is the different parameter variation. Okay, the different parameter variation of the meandering structure and the split ring and this modified ground plane structure. So we can able to change the resonance frequency of the particular band here. So this is the fabricated the antenna front view and the bottom view. And the radiation characteristics we are not showing here. If you see the radiation characteristics of three band, so we can able to get the a consistent radiation in all three bands. So even though if we are changing the radiation, even though we are changing the resonance characteristics, the radiation we can able to get that the consistent radiation pattern. So similarly, we can able to get the multi-band circularly polarized antenna loaded with split ring resonator and copper strips here. Okay, this is the simple, again the simple conventional slot antenna here. This conventional slot antenna is loaded with metal strips as well as the split ring, modified split ring here. The split ring is modified to like this way. Then we can able to get the triple band operation. Okay, the one band is coming from the slot, other band is coming from this strips, and the third band it is going to coming from the split ring. Okay. So all those things are getting excited using the feed. Then we can able to get the triple band. So in this triple band, so we can able to get some of the band, we can able to get the circular polarization, and some of the band we can able to get the linear polarization. So all the configurations, so we can able to achieve here. So here we are showing that all the bands we can able to get the circular polarization. To get the circular polarization, we are using this kind of uh, split ring. Okay, the split ring, the modified split ring, the inner ring we are modifying to get the circular polarization. If we are keeping the conventional split ring, so we are going to get the particular the third band we are going to get the linear polarization. If you want the circular polarization, we can use this kind of modified split ring. We can get circular polarization. This 45-degree orientation of the this strips, metallic strips, it is going to give the circular polarization in the middle center band here. Okay. So all these three band we can able to get the circular polarization using this compact split ring and metallic strip loaded slot antenna. This is the radiation efficiency and the gain and the radiation pattern at the three different frequencies, center frequencies of the band, double band antenna. So similarly, we can get the tri-band circularly polarized antenna using that modified split ring. Okay, here we are making that the splits more splits are making in the outer ring and as well as the inner ring. So using this kind of modified split ring loaded the slot antenna, so we can able to get the tri-band CP antenna, circularly polarized antenna. Okay, this is the return loss plot, the axial ratio plot, and the gain and radiation efficiency characteristics here. So the next one is the we are loading the corner expanded slot antenna with this kind of metallic strips. Okay, the metallic strips the loaded with the metallic strip. The slot antenna is loaded with the metallic strip of this kind of shapes. Okay, this is the unit cell of the metallic strip. These metallic strips are loaded with this corner expanded slot antenna to get the dual band circularly polarized antenna. So this antenna is going to give this kind of characteristics, the dual band nature. Both the bands we can able to get the circular polarization. Okay. So circular polarization, it comes from that this kind of shape, the strip shape, as well as the corner expansion. Okay. So we know that in the conventional microstrip antenna, if you want to get the circular polarization, so we have to do that corner truncation. Okay. So opposite effect we tried here in slot, we expanded the corner instead of truncation, we expanded the corner so that we can able to get the circular polarization. So we tried in this configuration here. Okay. This is only the corner truncation, the corner expansion here. Okay. The corner expansion opposite to the microstrip patch antenna in the slot, we did the corner expansion. This corner expansion, it gives the circular polarization at one single resonance frequency. So with this antenna, we roll it with this kind of metallic structure, so we can able to get the circular polarization at dual bands. These are the radiation characteristics of the antenna here. So we can able to design the compact wideband slot antenna loaded with split ring resonators. Okay. So this is the simple slot antenna here. This slot antenna is loaded with split ring resonator. Okay. So if we want to get the compact antenna, so what we can able to do, we can able to, it is going to offer the some symmetry. Okay, this antenna. So we can able to get the same kind of performance of this slot antenna or the reduced length antenna also. Okay, this antenna is a half length of this antenna, but due to the symmetrical nature of this antenna, so we can able to get the similar characteristics of this antenna. So even though if the length is reduced to half, the antenna resonance frequency is similar to this antenna here. Okay. So by loading this kind of slot into the reduced length antenna or the compact antenna, so we can able to get that the dual resonance characteristics here. Okay. So you can see here that this is the conventional slot antenna. It is going to give the single resonance frequency. By loading the SRR, we can able to get the additional resonance frequency compared to the, in addition to the slot resonance. So this is the conventional slot antenna loaded with SRR. So by symmetrical nature of this slot antenna, if you are going to remove the half of the slot antenna length, the resonance characteristics is not going to change. So that's what here we can able to see this one. So this antenna resonance characteristics and this antenna resonance characteristics mostly same, but the length is reduced to half. So in the reduced length antenna, if you are loading with this SRR structure, then we can able to get the additional resonance frequency. Then we can have the dual resonance antenna, dual band antenna here. So this is the electric field distribution or surface current distribution of the antenna SRR loaded antenna with two different resonance frequencies. At 5.5 gigahertz, SRR is getting resonated. At 2.4 gigahertz, this slot antenna it is going to resonate here. So as shown here. Okay. So this is the variation of the parameters of the slot and SRR. So we can able to vary the resonance frequency of the two bands. This is the fabricated structure of full length slot and the compact slot antenna here. Okay. This is the measured results, and this is the gain and efficiency at two resonance frequencies. Okay, these are all the some of the measured radiation patterns at the two different resonance bands. So we can here we tried that using the modified SRR like this structure. So we try to get the tri-band operation using the compact slot structure. So using the modified SRR structure, we can able to get the one more additional resonance in the slot antenna. So we can able to get the tri-band compact slot antenna. Okay. So the next one is using the metamaterial structures, we try to design the dual polarized MIMO antenna. Okay, so we know now that one of the enabling technologies for the 5G communication is the massive MIMO configuration. So in the massive MIMO, the antenna should be placed close to each other. So the isolation between the antenna we need to improve. Okay, the mutual coupling we have to reduce. As well as we have to get that the compact the antenna structure. Okay, so we tried here the dual polarized antenna. Okay, the dual polarized means, so you see here that the orange color structure, it is going to give one kind of polarization, linear polarization, and this blue color, it is going to give the another polarization here. So this is the simple dipole antenna. This is a crossed dipole antenna. Okay, so this is one dipole antenna. This is another dipole antenna. Two crossed dipole antennas are there, and we are using the feeding structure, appropriate feeding structure. So this dipole antenna is going to radiate the dual polarized case, the MIMO antenna. Okay. So this antenna we are keeping close to each other. So we need to reduce the mutual coupling. So for that, we are using this kind of the SRR structures to create the band gap so that we can able to improve the isolation between the two antennas. Okay. So this is the characteristics of the unit cell of the this SRR. This SRR structure is going to give some kind of uh, the band, some kind of band stop characteristics. Okay, so the between the port 1 and port 2, so we can have that S11 and S21 the characteristic it is shown here. So it is going to stop the wave propagation from port 1 to port 2. So this structure we are going to place between the antennas in the array, then we can able to improve the isolation between the antennas. So this is the feed structure for the two antennas. Okay, the two dipole cross dipole antennas, and this is the isolation element we are going to keep. So the performance of the these SRRs on the isolation. So it is simulated using this the surface current distribution. So when this structure, the SRR structure is not there, so what it is going to happen? We have the mutual coupling between the adjacent antenna element. Okay, so the isolation we can able to improve by keeping this kind of this band stop arrangement structure. Then we can able to improve the isolation between the antenna elements. So the antenna characteristics of the MIMO antenna characteristics we can able to improve. This is the fabricated structure. Then these are all the results of this crossed dipole. Okay, we are keeping the naming of this antenna 1. Okay, the antenna 1. This is the cross dipole 1, cross dipole 2, like that. So we are keeping the different name, the isolation and the S parameters of the different elements. So with this structure, the SRR structure, without SRR structure, so we are compared, and it shows that good isolation between the antenna elements when these SRR structures are loaded. Okay. So the isolation without SRR loading, we are having the 20 dB. So with SRR loading, we can able to improve that 5 dB improvement. It is there. So between the elements, and the maximum of the 10 dB improvement, it is there with the adjacent elements. Okay, that kind of isolation improvement we have achieved the MIMO antenna. So this is the summary of the MIMO antenna configuration. Okay. So So the isolation of 30 dB between the two ports, we can able to get the gain of 5.5, 7.5 dB we can able to get, and the dual polarized also we are able to design with 45-degree cross dipole structure. So another improvement in the MIMO antenna is we try to use that high gain enhancement as well as the isolation. To improve the gain enhancement and to design the compact structure, we used the AMC, artificial magnetic conductor, in the MIMO configuration. Okay, so this is the dipole configuration, the crossed dipole. This antenna is loaded with the AMC ground plane. This is the AMC ground plane. This antenna is loaded. So we can get that better because of the AMC reflector, we can get the better uh, radiation characteristics and the compactness of the antenna we can able to get. So here we are using the frequency selective surface to reduce the isolation between the antenna element. So this kind of FSS structure we have used. This is the complete antenna loaded with the AMC as well as this FSS structure here. These are some of the antenna parameters here. So this surface current distribution shows that the effectiveness of the FSS structure on mutual coupling reduction. So in summary here, the AMC structure, loading and without loading structure, it gives the AMC surface gives the better performance compared to the conventional ground plane. Okay, the isolation, we are getting the better isolation. Then the gain also, we are getting that the better gain. Then the compactness also we are getting because the height of the antenna we can able to reduce. Okay, so these are all the advantage of this AMC structure along with the MIMO antenna, and the MIMO antenna loaded with this kind of FSS structure, so we can able to reduce the mutual coupling between the array element. So we can able to place the two antennas very close to each other. So the antenna height as well as the spacing between the two antennas we can able to reduce. So we can able to get that the very compact antennas. So using these metamaterial structures, still we can able to get that future, we can able to get that the further characteristics enhancement for the antenna. So we can able to get the electrically small the antenna we can able to get. So we can able to design the miniaturized antennas, okay, using the metamaterial inspired structures. The gain also we can able to improve. Okay, so using that non-zero refractive, near zero refractive index surface and the graded refractive index lenses. So this kind of structures we can able to use. So further still the gain enhancement we can able to get. Similarly, that isolation, the mutual coupling reduction also we can able to improve the beyond minus 100 dB the level using this kind of metamaterial structures. Okay. The the conclusion. So we have seen that using the metamaterial structures, we can able to design that the polarization conversion, the miniaturization, compact antenna with multi-band operation, then the circularly polarized antenna, the multi-band circularly polarized antenna we have seen. Then we can able to design that MIMO antenna with uh, the compact MIMO antenna with improved isolation also we have seen. So this kind of antenna characteristics improvement we can able to design and we can able to get using the metamaterial structures. So that's all from my side. Thank you. So if you have any questions, we can able to answer.
Thank you, sir. Thank you very much.
Yeah, thank you, madam.
So it was truly inspiring to hear about your research and innovative contributions in this field. Thank you once again, sir, for your presence and contribution.
Yeah, thank you. Thank you
Thank
for the listening and thank you for the opportunity given to present the topic of metamaterial antennas. So if you have further any queries or related any help to design or fabricating the metamaterial based antennas, so you can contact me. So you can get my contact details from the organizers or you can take from my website also from the department, my department website. Thank you. Thank you for one and all. Good night.
Sir, there is one query in the chat box. Can we
Okay.
do fabrication for terahertz frequencies?
Yeah, terahertz actually the structures it is going to be very very small. So uh, yeah the terahertz if you are going to design that the metamaterial structure or antenna structure it is going to be there uh, in the micrometer range. Okay. So for that the conventional fabrication technique we cannot use like etching or anything. So we can go for either the 3D printing technique or additive manufacturing kind of thing or any that whatever we are using for the photonic circuits or the VLSI circuit microelectronic circuit concept, those kind of fabrication technique only we have to go if we are going for beyond certain frequencies. So conventional technique we can go up to 70 gigahertz for the fabrication technique. Like whatever the we are etching technique we are using our PCB fabrication technique. So we can go up to 70 gigahertz. So beyond that, it is very difficult. And whatever the connectors we are using, all those things, it is difficult at the terahertz.
Sir,
So
one more
people,
query.
yeah.
Is it possible to control the angle of radiation using the edged metamaterial design?
What is that? Edged metamaterial design.
Yes, sir.
So what is edged metamaterial? I'm not getting that the proper this thing. What is edged means? I am not getting here.
Professor Nitin, can you unmute and ask your query?
Yeah, good evening, sir. My name is
Yeah,
Nitin Matthew.
yeah, good evening.
So, sorry if I did not properly, use the proper term. In one of the slides where you showed that when you move the edges, the design that you use, move the edges to,
Okay, okay.
yeah,
So this one,
the
okay,
angle
that
of radiation tilted to 45 degree. So I wanted to ask if same can be used to, have variations
so
in such.
you are telling about this design, no? This one.
Yes, sir. Yes, absolutely.
Okay, okay, fine. So here, what you are asking?
So here you mentioned that on the far right side, two columns of we shifted it to the right edge, right? And the angle of radiation it tilted to 45 degree towards right. Now, is there any possibility that by controlling the center of that those designs, can we shift it to other angle other than 45-degree or any other direction?
Yeah. It is possible. Suppose here you see the right side of these two columns we have shifted. We are from center to edge actually.
Yes,
Okay,
sir.
so that radiation we are tilting towards this one, that from the z-axis we are shifting towards the right side. Suppose if you want to tilt the beam towards the left side of this z-axis, then what we have to do, this side, the left side, these two column, so we can able to shift the vias from center to the edge. Similarly, if you want to tilt uh, forward direction or in the backward direction, so then accordingly the this side vias we can able to shift, that top and bottom vias also we can able to shift from center to the edge. Then we can able to tilt the beam.
Okay, thank you, sir. And
So
one more thing, if we
all four direction we can able to tilt. So
okay,
which direction we are going to tilt we are shift the vias, so that direction it is going to tilt the beam.
okay, sir. And but does that compromise with the gain that we get?
Yeah, compromission means my 2 dB gain reduction. Yeah, 2 dB gain reduction we got compared to the this one, the broadside direction, the tilted beam. It is giving the 2 dB gain reduction.
Okay, sir. Thank you so much.
Okay, thank you. Is there any other question, madam?
Yes, sir. Which type of metamaterial or which metamaterial suitable for MIMO antenna design?
Yeah, MIMO antenna, we showed here the two examples here, the two design. And the last two design we showed for the MIMO antenna. The MIMO antenna, mainly the metamaterial structure we are using for that isolation improvement between the array element. Okay, so band gap structure or some frequency selective surface to reduce the isolation or to reduce the mutual coupling, to improve the isolation or reduce the mutual coupling. So we can use the metamaterial structures in the MIMO antenna. Is there any other question, madam?
No, sir, one more query.
Yeah.
How can we apply AI to MIMO?
So I am not working anything in that with the AI actually. So we are planning in future. We want to use AI to optimize the antenna dimensions or antenna characteristics. This kind of thing we are planning in future. But till now we are not trying anything with the AI with the antenna design.
Okay, sir. Thank you. Sir, one more query available.
Yeah.
How to
Yes.
consider electrical length variation with respect to metamaterial structure?
Yeah.
How to
Consider the
consider?
electrical length variation. Huh?
Yes,
Yeah, so as I
yes, sir.
showed in the first slides, the metamaterial introduction. So the if you are going to change the electrical length of the any metamaterial structure, okay. So basically you can able to shift that effective parameter, the negative epsilon, negative mu values to the different frequencies. Okay, so the metamaterial characteristics, that what are the characteristics are there, that negative mu, negative epsilon. So you are going to achieve that. It is depends on the dimensions related to the wavelength. Okay, so accordingly, so you are going to change the length of the structure, so the characteristics is going to shift to the different frequencies. So here, so this is the wavelength related structure, all the characteristics.
Sir, one more question.
Yeah, yes.
How to decide position of the metamaterial, like as straight or in the same plane or below the antenna? Can we get gain enhancement by 2D metamaterial structure?
Yeah. So that the superstate means the superstate. The purpose is to improve the gain, or the simply it should not affect the radiation. Suppose if you are using some radome structure for the antenna, so it should not affect the any radiation. So in that case, so it should pass the wave. The transmission, it should pass without any reflection. Okay. So if suppose if you want to use the for gain enhancement purpose, so what it should be the metamaterial unit cell characteristics. So it should give the transmission characters, transmissive characteristics, as well as some beam focusing characteristics. So those kind of structures we can use it for the superstrate. Then we can able to improve the gain of the antenna. Okay, while the radiation from the antenna while passing through the structure. So because using because of the metamaterial structure, the electromagnetic wave get focused in the far field. So we can get the gain improvement. This is one application for the superstrate. As well as we showed some of the one of the antenna, that is the polarization conversion. Okay, so we can use the metamaterial structure as the superstate, and the electromagnetic wave coming from the antenna pass through the structure, so we can get the polarization conversion. Okay, so it won't affect the radiation, but it's going to convert the linearly polarized wave into polarization conversion. So if you want to put the metamaterial structure along with antenna plane, so then some band gap structures. Okay, so some band gap structures, some band gap applications are there. So this kind of structure we can keep along the antenna dimension. Suppose if you want to keep the below the antenna structure, like as the ground plane, then the artificial magnetic conductor characteristics, any electromagnetic metamaterial structure, it gives the uh, artificial magnetic conductor behavior. Okay, then we can replace with our metallic conductor with the AMC structures, then the antenna characteristics will get improved. So it is based on the application, and it is based on the characteristics of the metamaterial unit cell structure. So we can able to decide. So where we can keep it is a superstrate or along the antenna plane or the below the antenna. So all the placement we can able to decide.
Thank you, sir. Thank you very much for spending your valuable time.
Yeah, thank you, Yonandal. Thank you for listening. Thank you.
Thank you, all participants. The feedback link is shared in the chat box. You can fill it before 10 o'clock. Tomorrow's session will be handled by Professor Arun Kumar from NIT Warangal. Both the sessions will be handled by him. He will be handling the session related to reconfigurable antenna design technique. First session tomorrow, 6 to 7:30. He will give an overview of reconfigurable antenna design, and he will show a demo in HFSS software, reconfigurable antenna design. Do join. Thank you all for your active participation.